we now have a formula for what the dimension of m sub n is in terms of the dimension of m sub n0. And as it turns out, calculating the dimension of m sub n0 turns out to be easier than calculating the dimension of m sub n. So that's what the goal for this video is going to be, is to calculate the dimension of m sub n0. Okay. So why would this be any easier? Well, let's take some, okay, well this would be a 3 in this case. So let's take a 3 by 3 magic square where the magic number is 0. So if the magic number is 0 for this matrix, then that tells me, the fact that this is a magic square to start with, tells me that there are a bunch of equations that are satisfied here, a bunch of linear equations at that. So, all right, so each row has to add up to 0. The magic number is 0. So a plus b plus c, d plus e plus f, and g plus h plus I, all of these have to add up to 0. Additionally, each column has to add up to 0. So I'm spacing these out so that we can put this into a matrix a little bit easier in a bit. But I would have each column adds up to 0, so a plus d plus g, so a, d, g, and then b, e, and h, and then c, f, and I. All of those have to add up to 0. And you see that I'm just like lining up all of the variables so that the f's are above the f's and such, because we're about to put this into a matrix. And then I have 2 more. I need to have the diagonals add up to 0 as well. So I need a plus e plus I and c plus e plus g. So a, e, I, c, e, g. All of these have to add up to 0. Okay. So we can put this into a matrix, which we'll call A here. And this is what it looks like. Maybe I'll zoom out a little bit so you can see what's going on here. So A, B, C, that goes to a 1, 1, 1, and everything else is going to be 0. And then similarly for D, E, F, we have 3 1s right there, and then 0s everywhere else. Same for the third row. Second row looks like this, and then the third row corresponding to the diagonals looks like this. Okay. So let me zoom back in. Okay. So the dimension of m sub n0, you might have noticed already, is equal to the dimension of the null space of this matrix. Because if we are saying that that all of these equations are satisfied, so we're looking at putting a whole column of 0s on the right here. So the set of solutions to the homogeneous system that this matrix represents is exactly the null space. It's the set of solutions to ax equals 0. So the dimension of m sub n0 is equal to the null space of this matrix A. Let me just... Okay, great. So if we want to calculate the dimension of m sub n0, we've reduced that to calculating the dimension of this this matrix. So I have done this for a 3 by 3 matrix, and not 3 by 3 matrix, but for a matrix coming from 3 by 3 magic squares. The size of this matrix here is actually 8 by 9. And in general, for m sub n0, this matrix is going to have, so it's going to have 2n plus 2 equations and n squared variables. Why is that true? Well, you're going to have, so in this case, we had 3 rows. We had one equation for each row, and there were 3 rows. We had one equation for each column. There are 3 columns, so we have 3 plus 3, and then we have 2 diagonals. So if we're doing this for an n by n matrix, then we would have n rows, or n equations for each row, plus n columns, n equations for each column, plus, and then we would still only have 2 diagonals. So we would have 2n plus 2 equations. And how many variables? Well, we would have 1 variable for each entry of the matrix. And if this is an n by n matrix, then we would have n squared entries, as we talked about in the first video. So this is going to be a 2n plus 2 by n squared matrix. That's going to be the size of it. Okay. The idea here, we're going to look to the rank-nullity theorem again to calculate the nullity. So we're going to calculate the rank of this matrix and use that to calculate the nullity. So what's the rank of this matrix? Well, first thing you might notice, so let me just show you this for the 3 by 3 case, and then I'll tell you that it generalizes very easily to the n by n case. If I add up all of the first 3 rows, and then the next 3 rows, I should get the same vector of all 1s. So if I add up the first 3 rows here, I get 3 1s from there, 3 1s from there, 3 1s from there. And then if I add up the next 3 rows, I would get 3 1s there, 3 1s there, 3 1s there. So both the first 3 and then the second 3 are going to add up to a vector consisting of all 1s. So I have that here. Row 1 plus row 2 plus row 3 is equal to row 4, row 5 plus row 6. In other words, the rows are linearly dependent. You could even write row 1 as equal to, if you wanted a strict linear combination of the other ones, you could subtract rows 2 and row 3 over. And this is a linear dependency. So the rows are linearly dependent. But as it turns out, if we omit one row, just throw out one of them, the set of rows will be linearly independent. This is pretty hard and time-consuming to show, and I don't think it's particularly worth it to go through the calculation for this video, but it is in the book. So if you are interested in why the rows would be linearly independent, I would strongly encourage you to read through the proof of this statement in Hefferson's book. So anyway, because of that, so the rank of A is going to be equal to the row rank, right? There are 2n plus 2 rows, and we have to omit one of them for the rows to be linearly independent. But when we do get a linearly independent set. So we have 2n plus 2 rows, we throw out one of them, and we were left with 2n plus 1 linearly independent rows, and so the rank of A is going to be 2n plus 1. Okay, so by the rank nullity theorem, what do we get? So I get that the rank of A plus the nullity of A is equal to the dimension of the domain of any map that A represents. So A is a 2n plus 2 by n squared matrix. So I have 2n plus 2 and then n squared. If I were to multiply by a vector, how many entries would this have to have for this matrix multiplication to make sense? Well, there would have to be n squared, because you're multiplying one row, which would have n squared entries, times this column, which would have n squared entries. So the inputs for a map that this matrix would represent would have n squared entries, and so the dimension. So this would represent a map from Rn squared to R2n plus 2, for example. So the rank plus the nullity is equal to n squared. Okay, and then we just pseudo calculated that the rank is equal to 2n plus 1. And we also said that the nullity of the matrix is equal to the dimension of m sub n0. And so now I can just subtract and conclude that the dimension of m sub n0 is equal to n squared minus 2n plus 1, or minus 2n minus 1. And what's more, we can also apply what we said before and say that the dimension of Mn is equal to the dimension of Mn0 plus 1. And so this should be n squared minus 2n minus 1 plus 1. And those are going to cancel, and we're left with n squared minus 2n. I was a little confused. I think this is probably a typo. In the book, they said that it's equal to n squared minus n. Maybe I'm misunderstanding something. Maybe I'm missing something, but I think that was a typo. If you think that I'm misunderstanding something and you notice that the book did not have a typo there, that it's really supposed to be n squared minus n, let me know in the comments below. I'd be interested to hear. But anyway, so the upshot of all of this is that we can count how many n by n. Oh, also, I should have mentioned this from the start. All of this is for n greater than or equal to 3. For n equal to 1, the dimension is equal to 0. So I guess this this would not work, because if I plugged 1 into this, then I would get 1 minus 2 minus 1, so that dimension would be negative. That doesn't make sense. And for n equals 2, what do we get if I plug in n equals 2? We'll get 4 minus 1, and that would also be negative. So you can't apply this theorem to for n greater than or equal to 3. For n less than 3. So n has to be at least 3 for these formulas to work out. But as it turns out, for n equals 1 and n equals 2, the dimensions just end up being 0. The book talks more about that, and there's actually an exercise that goes along with that that I think is worth